All right, so what we're going to talk about here is just a little bit of a expansion on the atomic structure stuff that we talked about yesterday. Okay, we're going to look at the configurations of electrons. We talked a little bit about that at the end of the day. I talked about those little orbitals, those weirdly shaped things that were in that last diagram, right? There was one that was kind of a circle, and then there were these kind of teardrop shaped ones that were around that. We're going to look at those a little bit. We're going to look at what isotopes are. How many people have heard that word before? Okay, so what we're going to look at is that even though we said in Dalton's atomic theory that every atom of oxygen looks the same, it isn't really true. Okay? There are actually isotopes, which is slightly different versions of oxygen or slightly different versions of carbon, okay, or whatever, that are slightly different. Not in the number of protons, because if they had a different number of protons, they'd be a different element. Okay? But in the number of neutrons. Right? For example, hydrogen, normal hydrogen, the most common form of hydrogen, okay, has one proton and one electron. Okay? But occasionally you will have hydrogen atoms that have a neutron as well, okay, or even two. All right? And we call that deuterium. All right? Because it has neutrons in it. All right? It's not just hydrogen now, it's something else. It's still got basically all the same physical properties as regular hydrogen does, it's just heavier. Okay? How many people have heard of carbon dating before? Okay, so carbon dating is a form of radiometric dating that's used to figure out the age of artifacts and things like that. Okay, it's based on the fact that most carbon atoms, okay, they have 6 protons and they have 6 neutrons, right? But there are some forms of carbon that have an additional 2 neutrons, and they're heavier. Okay? We call them carbon-14 because they have 14 particles in the nucleus. Okay? 6 protons, 8 neutrons. Right? Everyone follow me there? Now, those isotopes tend to break down radioactively. Not enough to cook you, okay? But they break down radioactively slowly at a very predictable rate. So what they do is they look in artifacts for the amount of carbon-14 that's in there versus the amount of carbon-14 that would be in something that's brand new. Okay? And from that difference, they can calculate how old that material is and how long it's been exposed to the air based on how much carbon-14 is left. Okay? Versus how much of what it breaks down into is present. Okay? All right, so we're going to look at what isotopes are and their importance. We're going to learn and understand the ideas of Bohr on the structure of the atom, because we said even though we accept the electron cloud model, some of Bohr's ideas are still pretty good. Follow the progression from Bohr's model to the quantum mechanical or electron cloud, that's de Broglie's model, okay? And understand how the periodic table reflects those ideas, and we're going to go through that pretty quickly. All right, so like I said here just a few minutes ago, okay, Dalton said all the atoms of each element are identical. Okay, we know now that while that's essentially true, the important particle always is the same, and that's the proton. Okay, number of neutrons can be different. Right? The example I gave you a few minutes ago was hydrogen. Okay, normal hydrogen we call, I don't know, I call it hydrogen, but they call it protium. Okay, it's got 1 proton, 1 electron. Okay. And then there's deuterium, which has a proton, it has a neutron, and an electron. Okay? And then there's tritium, which is extraordinarily rare. Okay? It has 2 neutrons, okay, 1 proton, and still 1 electron. Okay? Because the neutrons are neutral, it doesn't really matter how many of them there are. They don't affect the charges or anything like that. They just make the atom heavier. Okay? All right. All right, so we call those different forms, we call them isotopes. Generally, we don't give them fancy names like we do with the hydrogen versions. We just give them a number. Okay, like we don't have a fancy name for carbon-14 other than carbon-14. Okay, we have like uranium-238 and uranium-237, and okay, all the different isotopes are just the name of the element and the number of particles in the nucleus. Okay, so that's how we name them. All right, so to show the different isotopes, we write the chemical symbol for that element with 2 numbers to its left, okay? The mass number is the superscript, so the top number, okay? And the atomic number is the subscript. So if we're looking at lithium, lithium has how many protons in it? 3. All forms of lithium have 3. If it had 4, it would be beryllium. Okay, so the other number then is, okay, here's the total mass number. How many particles are in the nucleus? So in this lithium, there's 3 protons and there's how many neutrons? 3. Okay, and in this one, there's 3 protons and there's 4. Okay, so we got it. It's pretty straightforward, right? Okay, that's how we write those generally. Okay, and you can see down here they've got the pictures, okay, of what that atom would look like. So 3 neutrons, 3 protons, 3 electrons, 4 neutrons, etc. Okay, the atom, sorry, just gets bigger. Okay, and then obviously we give them the name of the element with the number of particles. So this stuff would be lithium 6, this would be lithium 7, and this would be lithium 8. Okay. All right, so the atomic mass of an element reflects the weighted average. So if you look on your periodic table, you'll see this number here that's got all the decimals in it. I think yours is actually, on yours it's in the top right corner, sorry. Okay, here's in the top right corner. So if we're looking at lithium, for example, okay, the atomic mass of lithium is 6.94 grams per mole. Okay, we'll talk about moles way later on in the unit, but okay. That's the average of all the isotopes of lithium that there are. Right? Now, most lithium is the normal kind of lithium, okay, that has 7 particles in the nucleus. Okay, that's the most common variety. 3 protons, 4 neutrons. That's the most common variety. Okay, the other ones occur in such small amounts, okay, that they don't affect the average very much. So it's a weighted average. If normal lithium accounts for 99% of all lithium that's in existence, okay, the number there will be very close to the weight of that type. Okay, but it might have the extra decimal place on there because the other two, you know, their 1% affects it slightly. Okay, so essentially what we do, and you're never going to be asked to do this, but kind of just explain it here. Okay, if we have sulfur 32, okay, sulfur 32 has an atomic mass of 31.972 grams per mole. So a mole is just a unit of measurement we use for chemistry. We'll go into it much later, but okay. And it comprises 95% of all natural samples. So if I want to find out what's the average amount of everything, I'm going to take this number here, multiply it by 0.95. Okay, I'm going to take sulfur 33's mass and multiply it by 0.0076 because it only accounts for 0.76% of all the sulfur that exists. Okay, do the same thing with sulfur 34. Take its atomic mass and multiply it by 0.0422. Okay, and then multiply sulfur 36 by 0.000014. Okay, and then add all those numbers together. That'll give me the weighted average, and that's the number that'll be on the periodic table. Okay. Yeah, it's not something you're going to be asked to do, but if you're ever wondering why your numbers on your periodic table have less decimal places than the ones on the one at the front, it's because this one shows, like, basically it takes into account all those other ones. Okay, yours kind of shows less accuracy. Okay, moving on. So in 1913, Bohr talked about electrons and how they were arranged in concentric circles, okay, or orbits like the planets around the sun. Okay, he said, yes, electrons are attracted to protons, but they never crash into the nucleus. Okay, he said, why would you think they would crash into the nucleus? The Earth hasn't crashed into the sun. Okay, why would electrons crash into the protons? It doesn't really make any sense. If they move fast enough, they stay where they're supposed to stay, okay, and they don't crash. He proposed that electrons in a particular path have a certain amount of energy. Okay, thus they do not lose energy and crash into the nucleus. And the energy level of an electron is the region where it's likely to be. Okay, that's why we don't call them orbits. We call them orbitals. This is where it's probably going to be found. Okay. Okay, so the energy levels are like rungs on a ladder. If you're going to climb a ladder, do you have to do work to do that? Yeah, right? Which rung would you rather fall from? The first one or the top one? Yeah, you'd rather fall from the first one because you probably won't get hurt. Okay? Because the higher up the ladder you go, the more energy you've had to put into that, and thus the more energy you would have if you fell off and crashed into the ground. Right? Well, it's the same for electrons. The further away from the nucleus they get, the more energy they must have. Okay? And then, conversely, the more energy they could give off were they to start moving back towards the nucleus, which we know that they do, and we talked about that fluorescence stuff yesterday. Okay? All right. So an electron can only be found on a path, not between them. So you're either, it's just like a ladder. You're either in this orbital or you're in this orbital, but you're never going to be in between them. Okay? Last time I checked, you can't stand in between the rungs of a ladder. Okay? Unless you're on the International Space Station, then I suppose you could, because there's no gravity to pull you down to the other rung. Right? But on Earth, anyway, you can't stand between the rungs. Okay, you have to stand on one or the other, and the energy levels for the electrons are the same thing. All right. Yeah, so they're kind of showing the same thing here to do with energy and speed of movement. Okay, they're comparing, the nucleus would be like a parking lot. Okay, First Street would be, a road in town where you can maybe only go 40 kilometers an hour. Okay, Energy Highway 8 would be like, leaving town out here where inexplicably you're only allowed to go 60. Okay, and then you get onto, Queenie, all right, to Highway 2 there, and you can go 110. Right, just there's more energy the faster you go. Okay, now this is kind of an interesting computer model of what the movement of electrons would look like around an atom. Okay, all the little kind of bright squiggly lines represent the path that an electron would follow. So where do you notice most electrons are located? Closer to the nucleus. Okay? They can't maintain the energy that's required to stay in the high outer orbitals all the time, right? So we see less and less of them, okay, out here. It's more likely that electrons will be filling the lowest low energy orbitals first, right, before they go and occupy the really high energy ones. Okay? If they're going to make the leap, okay, we call that a quantum leap from one orbital to another, okay, they have to gain sufficient energy to jump all the way, because like we said, they can't stand in between the energy levels. And you can almost see kind of those weird shapes that we saw yesterday in that diagram, kind of these teardrop shaped kind of orbitals here. Okay, so these are regions in which you could likely find electrons, okay? And then we've got some kind of weirder ones, right, that go out this direction here, okay? There's some bigger ones that go kind of further out, okay? And they all have really odd shapes, which we'll look at here in a little bit. Okay, so like the Bohr model, the cloud model or quantum mechanical model, okay, talks about energy levels for electrons, okay? It's just that the quantum mechanical model doesn't say it's here and there and there. Okay, it doesn't define the orbits. It says orbitals. Here's an area where a high energy electron would occupy. Here's an area where a low energy electron is likely to occupy. It's going to be somewhere in there, not right there. Okay, that's the difference between Bohr's model and the cloud model. Okay. All right, so that's why we kind of have those blurry kind of shapes. And here again, you can see there's that shape I was trying to draw. Okay, right in there. Okay, here's kind of some smaller ones, and then there's higher ones, okay, further on out. Okay, so here's what the orbitals kind of really are idealized, at least, to look like. Okay, in the quantum mechanical model, the energy levels of electrons are designated by numbers. Okay, and that number is always an integer. That's a whole number, right? You can't have level 1.5 because you can't be in between the levels. All right, so the first orbital is 1s. One that's closest in, okay? Pretty much just a circle, okay? And then you've got the next level here, okay? And so electrons, obviously, they can't all just jam into this one. Why not? Why can't electrons all just jam into the lowest orbital? Well, actually, you can hold 2, but why can it only hold 2? Why can't I put more than 2 in there? Well, I suppose it's possible they could crash into each other, but all electrons have what charge? Do they want to be crammed together? No, they don't like each other. They repel each other. Okay, so there has to be these strange shapes in order to create spaces where the repulsion isn't great enough to cause electrons to go flying off, okay, or do crazy things. So that's why you can see they're all kind of offset. We've got this first one that's a circle, and then these two would kind of be like here and here, and these two would be there and there. Right? And then these next ones, okay, kind of fill this. It's got that really weird shape. It's kind of like this, okay, kind of in there, and then you'd have that bubble and that bubble. And you see that we're creating spaces where there's not going to be a lot of overlap, okay, and the repulsion problem won't be so big. Basically, each orbital can kind of hold two, okay, each one of those spots. Right? And the further away you get, the funkier the shapes get. Okay, simply because they're higher energy, they're farther away. Okay, the electrons have to have, they have to be behaving very erratically to get out to those places, so they're going to have kind of crazier shapes. Okay, and then when you get to Chem 20, you'll talk about actually identifying the electron structure of each particular element. Okay, and then you write that down as this one. If you had a really big atom, you would have like 1s, 2p, 3d, 4f, 5g. You'd write out all the essentially orbitals that would be full. Okay, if we're talking about hydrogen, it's basically going to be 1s, okay, or 2s, okay, or something like that. Okay, so again, this is kind of the same thing here, just showing you how those orbitals get offset, okay, so that they can't, and it's three-dimensional, right? We got an x, a y, and a z axis, which is hard to draw, okay, but there's 3 dimensions in which they can occupy. Okay, so electron configurations. This is what I was telling you you'll do in Chem 20, but just to kind of show you what that means. Okay, there's a few principles that you use to kind of fill things in. Okay, the ways in which electrons are arranged around the nucleus are their configurations. 3 rules govern the filling of atomic orbitals. Okay, by electrons with the principal energy level. So the first thing is the Aufbau principle. Electrons enter orbitals of the lowest energy first. Okay, when you're climbing a ladder, you don't jump to the 5th rung from the ground. Okay, or you probably would fall. Right? You generally climb up from the bottom rung up the ladder as you go. Okay, so you'd fill this level first. All right, and then you would go to this level, and then to that one, and then you'd move here. Okay, and so on. The Pult exclusion principle. An atomic orbital may contain, at most, 2 electrons. Okay, because if you try to put more in any particular orbital, they'll repel each other too much, okay, and then the structure will become unstable. And then there's Hund's rule. Okay, when electrons occupy orbital, 1 electron enters each orbital at each energy level before they pair up. Okay, so if I'm looking at hydrogen, for example, hydrogen has 1 electron, so it would have a 1s configuration. Helium has how many electrons? 2. Okay, so it's going to be probably 1s, and then it'll fill one of these before any pairing happens, right? We don't want to pair anything up if we can avoid it, okay? And then, okay, and so on and so on. So the more electrons you got, you fill the lowest energy level first, okay? So you go, sorry, it wouldn't go 2p, it would go 1s, then 2s. Now that lowest energy level is full. Your next thing up, which would be lithium, would be 1s, or would be 2s, and then probably 2p. And then, and so on. So you'd fill with 1 before you move to the next level. Okay, so each thing in here has to have 1 electron. So each thing in level 3 has to have 1 electron in it, okay, before you can start pairing them back up. Okay. All right. Okay. Yeah, we kind of already talked about that. We'll just move on from there. And since we don't have to write electron configurations, we're going to skip that one too. Okay. Arrangement of the periodic table. I don't know if you talked about this in Science 9 or not. Okay, but there's kind of different groups. The periodic table is called the periodic table because it's based on how certain characteristics occur periodically. Okay, so everything that's in this first column here in group 1 is an extraordinarily reactive metal. Now, I know that seems weird because hydrogen's at the top of that group, okay? But hydrogen, even though it's a gas, is metallic. Okay? It behaves in a metallic fashion. It wants to give up electrons like crazy. Okay? It reacts very violently with lots of things. That's why we don't fill blimps with it. Okay? You guys know what the Hindenburg was? Okay? The Germans had all those Zeppelins and they filled them with hydrogen gas. Bad idea. Okay? Hydrogen gas, while very light and very buoyant, is also highly explosive. Okay? The slightest little spark, which happens when static builds up inside a big balloon, okay, yeah, it can lead to tragedy. So generally, balloons are filled with helium, which is completely inert. Right? So you don't have to worry about it. So all of these have similar properties. Okay, everything in group 2A. Okay, they're metallic, they're soft and silvery. Okay, they're somewhat reactive, but not nearly as reactive as the things in group 1. Okay, the things in group 1, like for example sodium and potassium, if you plop them into water, they explode. Okay, they're that reactive. Okay, in fact, we used to have sodium and potassium in the lab room, but we don't have them anymore. They have to be stored in a jar soaked in kerosene. Okay, so you essentially fill the jar with kerosene, which is the stuff you burn in a camp stove. Okay, and you put the sodium or the potassium in there, so it cannot come into contact with water vapor present in the air. Right? If you were to leave sodium out on the counter, okay, and on a really humid day, it could actually ignite. Right? It's that reactive, so you have to store it in something that doesn't have any water in it, like kerosene. So they're quite dangerous. We got rid of them because we never used them for anything, and if the jars ever cracked or something like that, we could have a fire. Right? And then basically all your transition metals here in the middle share kind of similar properties. Okay, you've got your metalloids, okay, and then you've got other groups here. I'm trying to remember all the names now. Basically just nonmetals, and then you've got your halogens, and then you've got your noble gases. Okay, sometimes they call those inert elements, but okay, generally they're called the noble gases because they don't react with anything. So on one side of the periodic table, you've got reacts with anything, and over here you've got reacts with nothing. Okay, and these occur periodically, and we try to group the things that behave the same together. Okay, and that was kind of the brilliant design of Mendeleev when he put this all together. We also find that everything in this column has a similar ionic charge. Okay, everything in this column is +1. Everything in this column is +2. Okay, everything over here is -1, -2, -3. Okay, and so on. So we got kind of these, again, these characteristics that occur, they get grouped together based on that. Okay. All right, so the modern periodic table, like we said, it's set up, okay, so that the things that occur periodically group together. Okay, terms that you'll hear me use, okay, just so you're aware, a family or group of elements, okay, is actually a column, okay, is a vertical column. Okay, a period is a horizontal row of elements because we see a change over the row. We see it going from very reactive to non-reactive. So there's a change, okay, or a cycling of characteristics along that row. All right, and anything that happens in a cycle, okay, has what's called a period. That's the time it takes for the cycle to complete. Okay, that's a physics term you'll learn in Physics 20. All right, metals are located on the left of the staircase, non-metals to the right of it, okay, and obviously on the periodic table I gave you, the staircase is that kind of darker black line there, okay, that separates metals from non-metals. Okay, and all periodic tables list the properties of the elements in their boxes, and there's a key for that right here on the top of your periodic table. Iron is the one that's in the key there, okay, and you can see that it's labeled. So the 26 there is the atomic number, the electronegativity is 1.8, the symbol is Fe, the name is iron, okay, the atomic mass, okay, is 55.85, and the most stable ion charges are 3 and 2 positive. Okay, so all of that is listed in there. Those are the important things that we need. Okay, groups of things that appear on your periodic table, noble gases, okay. We use noble gases in certain types of lights. You arc an electric current through them and they glow. Okay, so that's where neon signs, not all signs contain neon. Okay, they contain other noble gases. That's what creates the different colors. Okay, things like that. Okay, elements whose representative elements are the ones that behave normally. Okay, predictably. Those are the ones in the top part of the periodic table. Below that are the lanthanoids and actinoids, and they're different. Okay, they behave differently. Okay, all right. Yeah, the inner transition metals, that's the lanthanides and actinides, so they're down below. Don't worry about those. Okay, alkali and alkali earth metals. These are the ones I was telling you about, the first two columns of the periodic table. Okay, highly reactive metals, right, that are soft and silvery and gray. Okay, I think this is actually potassium here. Okay, beryllium, magnesium. You can see they all kind of look similar. Okay, some of them do have to be stored in other materials so that they don't react with anything. Okay, and then you got your halogens. Okay, so termed because some of the gases that are in the halogen group are used in halogen lights. Okay, different gases would produce different temperatures and thus different colors. All right. So you can see here we got fluorine. Okay, is clear and odorless. Chlorine is slightly green. That's the stuff that was used on the Canadian troops at Vimy Ridge. Okay, in World War I. Okay, they floated chlorine gas over top of them, and it causes your alveoli in your lungs to just constrict and you can't breathe. Okay, there's bromine, which is kind of a reddish liquid. Okay, iodine is actually a solid. You can get it in solution quite easily, and they used to use that to, and they still do, to kill bacteria at the site of injuries or surgeries and stuff like that. If you've ever had that put on, it stings a lot. Okay. All right, that's all there is for that. Perfect timing because we're almost out of time. Tomorrow is Thursday. What's going to happen on Thursday? Okay, I will post it later on today. It will be on lesson 1. It won't be on any of this stuff that we talked about today. Okay, so it'll be on structure of the atom, okay, people, places, okay, stuff like that. But the questions will be up there. Okay, I'll post them later on, probably this afternoon sometime.